Hey, Geometry, Chapter 6, Lesson 2, Bisectors of Triangles. Exciting time. So Section 1 covered some perpendicular bisectors and angle bisectors and some properties that deal with those in relationship to segments and angle specifically. Section 2 is now we're going to take those perpendicular bisectors and angle bisectors. We're going to do that to the sides of a triangle, and there's some actually fairly neat properties that show up with that. So remember that a perpendicular bisector cuts a segment in half and it is perpendicular to it. Okay, an angle bisector cuts an angle in half, and we're going to see that in some of the properties that we look at today. Some vocabulary before we get going. I'm going to get back on Desmos Geometry here in a little bit as well, and I encourage you to get that open as another tab and play around with it yourself and become familiar with it and more comfortable with it. Okay, so on page 171, the word concurrent. Okay, this word's going to show up through the next few lessons. Concurrent, this refers to lines that intersect at the same point. Lines that intersect at the same point, they can be referred to as concurrent lines. Okay? Lines that intersect at the same point. So we could have these three lines and they all meet right there at that point. These are concurrent lines. The point of concurrency, that is the specific location where the three lines meet. The specific location where the three lines meet. Okay, these next two here, the circumcenter and the end center, we're going to come back to that in a little bit. Okay, so I'm going to switch over here to Desmos Geometry. Encourage you to play around with this a little bit as well. And I'm going to draw a triangle. So I go up to the polygon tool. You can turn the grid on if you go up to the settings here and projector mode. You log in with your Google account, school Google account, that'd be the easiest way, and just click show grid. So if you like having the grid there like I do, you can turn that on. So when you click an operation, it tells you what you need to do here. So choose a point, choose another point, and choose another point. Okay, so choose another point or click an existing point to finish. So there's my triangle. I have my triangle. Now remember it stays on that function. So if you want to do something else, you have to go back to select, and now you can even move these around if you want to. Okay. So the first thing we're going to do is we're going to create perpendicular bisectors for this triangle. So for the three sides. So I'm going to select the side, and I'm going to go to More Tools, and I want to find a midpoint. There's a midpoint. There's a midpoint. There's a midpoint. So here, anything through this point would bisect it. And now I want to do a perpendicular line. So it says click a line to set the slope. So we click this line so it knows what slope it is. And there's that point. Do it again down here. So yeah, it keeps the same function. You can just do it 3 times. And look at that. Okay, these 3 lines right here, those would be the concurrent lines. Okay. And we have a point of concurrency that occurs right here. So they all 3 meet right there. And no matter how I move this triangle, okay, the point of concurrency always happens. Those 3 lines always meet in the same spot. Okay, isn't that kind of cool? No matter what you do. Now that point can be inside the triangle if you have an acute triangle. If you have a right triangle, notice it happens on the hypotenuse. And if you have an obtuse triangle, that point of concurrency is outside the triangle. Okay? Equilateral triangle would be right in the middle if we did that. So that is what happens when you have perpendicular bisectors. And that is what we're going to call now what we call the circumcenter. Okay? So the circumcenter, this is the name that's happening here. Okay, the circumcenter of a triangle is equidistant from the vertices of the triangle. So P is going to be referred to as the circumcenter. Okay, so I have perpendicular bisector DP, PE, and PF. And what that means is you have right angles right here. You also know that it bisects that from that, that from that, and that from that. And so this statement here, equidistant from the vertices of the triangle. What that means is the distance from P to B is a radius. And that's what's going to happen. That's why they call them a circumcenter. If you have a circumference, if you circumscribe something, okay, so there's lots of words that go with the prefix circum, like a circumscribe, circumference. I've already said that, and not getting two different places here. But what that means is P to B equals P to A, which equals P to C, and you can have a circle. That point P is the center of a circle that goes to the vertices. Okay? So you can draw a circle around there, and that point P is the center of the circle. So the circumcenter is the center of a circle that goes through the, oh, I'm sorry, you can't see that. Circumcenter, center of a circle that goes through the three vertices of a triangle. Center of a circle that goes through the three vertices of a triangle. Okay, I've actually used this in the shop sometimes because I had 3 points and I want to drill a hole that goes through those 3 points. I had to find the circumcenter of that triangle, and then that's where I knew to drill my hole. So if I have a hole saw, and it'd take out those 3 points perfectly. Okay, so the center of a circle that goes through the three vertices of a triangle. It is where the three perpendicular bisectors meet. So it's the point of concurrency for the perpendicular bisectors. Point of concurrency for the perpendicular bisectors. Let's put that down here. So P is the point of concurrency of the perpendicular bisectors. So when I go back to my Desmos diagram here, that means I can make a circle. I choose my circle tool. Here's my center, and I stretch it out to here, and you notice it goes through those three. A different color here, whatever we used. Gray, that's kind of boring. Red. Okay, and it goes through those 3 points. So the circumcenter is the perpendicular bisectors, where the perpendicular bisectors meet. It can be on the inside of the triangle. It can be on the hypotenuse of a right triangle, or it can be on the exterior of a triangle. See how that circle still goes through those 3 points if it's an obtuse triangle. So acute triangle that's on the inside, right triangle that's on the leg, obtuse triangle that's on the outside. Okay, so this is kind of cool. You kind of play around with it and move it around different places. Okay, the final thing on this category as I go back, okay, keep in mind that means P to B is the same length as P to C, which is the same length as P to A. Okay, so the perpendicular bisectors, those distances aren't the same, but the distance from P to the three vertices is the same. That makes a circle. So when we see questions like page 173, before we go talk about the next one, it says find the indicated measure. Okay, so you see this sort of setup here. You have a 90-degree angle, and you know it's a midpoint because you have two congruent sides. 90-degree angle, midpoint. 90-degree angle, F is a midpoint, E is a midpoint, D is a midpoint. Okay, so what that tells me is that P is what we call a circumcenter. Okay, that means there is a circle that goes through those 3 points. So P to B has to be 13, P to A has to be 13, that's what the question's asking, and also P to C has to be 13. Okay, so those all have to be 13. Now you notice on 5, you see the 90-degree angles, but it's not telling us anything about the sides being congruent. So this does not fall under the circumcenter theorem because it's not dealing with the sides being a midpoint. S, T, and U are not necessarily midpoints. It has to do with angles being bisected. When we look at GE, they want the length from G to E. Notice again, 90-degree angles and the sides are bisected. So you got to have 90-degree angles and the sides have to be bisected, which is what we have. So that makes, again, G a circumcenter. That means we have a circle going through all of that. So G to D is a radius. G to E would also be a radius of 10. And what's the other segment that would be a radius of 10? Would be G to F. That would also be 10. So again, look at 7. The 7 fall into the category as number 6. Are the sides being bisected? And we can see they are not. The angles are being bisected right there. So 8, 9, and 10. Find the coordinates of the circumcenter of the triangle with the given vertices. We're going to use some graph paper when we get to the actual assignment with this. So notice they don't put any axes on these. So find the coordinates of the circumcenter. So we need to create perpendicular bisectors. Now a little shortcut there is if you can get 2 of them and you do it correctly, you don't necessarily need the third one. Third one is just kind of a check to make sure you did it right. So my x values are -2, -2, and 6. So let's put my y-axis maybe right here. My y values are -2, 4, and 4. So we can just put that right there. So A is -2, -2. B is -2, 4. And C is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Okay, so we have A, B, C. We want the perpendicular bisectors. Horizontal and vertical lines are great. We love them because they're easy to count. So A to B, the midpoint would be 1, 2, 3, 4, 5, 6. So half of that is 1, 2, 3. So there's that. And that makes our perpendicular bisector go right there. B to C, 1, 2, 3, 4, 5, 6, 7, 8. So half of that is 4. 1, 2, 3, 4. Okay. So there's that perpendicular bisector. So this one would be right here. So that makes it at 2, 1. So that's the circumcenter there, 2, 1. So that would be the center of a circle that goes through those 3 points. Alright, see if you can get ahead of me. See if you can work faster than I do, but do it right. Okay? It's only good if you do it the right way. 3, 3, and 9. We better put it clear over here. It's my y-axis. 5, 1, and 5. Go down here. So 1, 2, 3, 1, 2, 3, 5. What's 1, 2, 3, 4, 5? There's D. 1, 2, 3, 1. And 4, 5, 6, 7, 8, 9. 9, 5. So there's F. Hey, another right triangle. That makes it easy peasy. So we're just going to find the perpendicular bisectors of the 2 straight sides. Just do horizontal and vertical sides. So this one is a length of 4. Okay, you know it's a right triangle. You probably already pick out where it's going to be. This side is a length of 6. So half of 6 is 3. 1, 2, 3. Shaboom, shaboom, 1, 2, 3, 4, 5, 6. 1, 2, 3. So 6, 3. That is the location of that circumcenter. And the final one, x values 4, 4, and negative 6. So 1, 2, 3, 4. Let's put it right there. And negative 7, negative 3, negative 3. So we need to put the x-axis up high. Okay, 4, negative 7. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. J. 4, negative 7. 4, negative 7. Down here. There's J. 4, negative 3. There's K. 2, 3, 4, 5, 6. 1, 2, 3. There is L. Yay for right triangles. Tell it's kind of the end of the day for me, can't you? Kind of whistling while I work. Makes the time go by quick. Okay, so K to J, length of 4. Half of 4 is 2, so 1, 2. Perpendicular line would be horizontal. Okay, I'm guessing it's going to be right there. Let's check this length. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 divided by 2 is 5. So 1, 2, 3, 4, 5. Vertical line, yes, right there. So that would be negative 1, 1, 2, 3, 4, 5. Negative 1, negative 5 would be that circumcenter. Okay, so there's the examples, everything with circumcenters. Remember, circumcenters are the perpendicular bisectors, and they create a circle that goes through all the points. Okay? So now we're going to go back. Let's look at page 172. We have the end-center theorem. So the end-center is different than the circumcenter. So a circumcenter is going to create a circle that goes around the outside of the triangle. Okay, the end center of a triangle is equidistant from the sides of the triangle. So this is going to create an inscribed circle. So what happens is if you cut this angle in half, and if you cut this angle in half, and you cut this angle in half, they all could be different halves because they're all different size angles. But if you do that, then where these points, this point of concurrency is going to be the same distance, blue doesn't work, same distance P to E, P to D, and P to F. It's the same distance. That makes this a circle on the inside. So that's what we refer to as an inscribed circle. It is in the shape, not outside the shape. So circumscribed goes around the outside like a circumference goes around the outside of a circle. Circle. There's a CIR, C prefix again. Okay, so inscribed circle comes from angle bisectors. So the three angle bisectors create an inscribed circle. And notice these distances are 90 degrees, but they aren't necessarily the midpoint. So this is not a midpoint. It can be at times, but it's not a midpoint right now. So on Desmos, what this looks like, this takes a little bit longer to make. And so I'm going to pull up a one that I've had before. So you see that green is the inscribed circle. So the end center is always inside the circle. Whoa, it doesn't like that. There we go. So the end center is always going to be inside the circle, whether it's a right triangle where'd that point go? Okay, whether it's a right triangle or not. I'll play around with that later. So that's the end center. Notice the 1.73s there. Those are the distances from the end center to the sides. They always stay the same. So when you go down to these, Okay, it's telling us the N is the end center of triangle ABC. Use the given information to find the indicated measure. So if this is the end center, that means you can draw this circle right there. So it's the same distance. That has to equal that, which has to equal that. They want the length from N to F, and they say ND equals NE. So we know ND has to equal NE. Get you some algebra here. So 2x minus 5 equals negative 2x plus 7. And go. I'm going to pick something up I dropped here. See if you can get that solved lickety-split. Add the 5 to the right, add the 2x to the left. That cancels. So 4x equals 12. X equals 3. You beat me. Kudos to you if you did. And if you didn't, keep working. Someday you will. Okay, now they want the length from N to F. So now we're going to take this and plug it back up into one of these. So 2 times 3 minus 5. That is 6 minus 5, and that is 1. So NF equals 1. So all of those have a radius of 1. So the end center inscribed circle has a radius of 1. Okay, all of these are kind of the same format here. N is an end center. They gave us NG and NH. They want us to find NJ. So x minus 1 equals 2x minus 6 minus the x. Add the 6, so you get 5 equals x. So x equals 5 is what you should get there. And so if you go 5 minus 1, you get 4. So NJ should equal 4. Go ahead and pause this, get number 3 done, and we'll get to the answer here in a little bit. Once you're done, come back and check. Did you get 7? I hope so. 7 would be the answer. That negative number threw me for a little bit too. It's like, oh, should supposed to get negative? But if you plug negative 3 into here, you get negative 2 times negative 3 is 6. 6 plus 1 is 7, so it checks. The radius is 7. Okay, P.S. This is what those angle bisectors look like. Okay, so that means in this case P is an end center. End center. It's an end center, so I'm envisioning a circle right here. P to S has to equal P to U, so P to S equals 8, same as P to T. Okay, NF has to be 2 as well. So again, you know that by the angle bisectors. That tells you that you have an end center, not a circumcenter like we had right there. Okay. So you'll want some graph paper handy to sketch some of these things when you have those questions. And remember, the end center is always on the inside of the circle. Oh, we never wrote that vocab. Not done yet. Sorry. Okay. So the end center is the center of a circle that is inscribed in a triangle. It is inscribed in a triangle. I'll spell triangle correct for you. Okay. This end center is always in the interior. Okay. The circumcenter there, remember that can be on the interior. If it's an acute triangle, it's on the hypotenuse if it's a right triangle, and it's on the exterior if it's on the obtuse triangle. So that takes care of lesson 2 there. Thanks. Keep up the good work, and we'll see you in class.